Hello, students. Very good afternoon.
Good afternoon, sir.
Good afternoon, sir.
Good afternoon, sir.
Very good afternoon. Let us wait for a minute as students are in the process of joining. Just convey a message to everyone that they join immediately. So we can start. Probably, if time permits, this Saturday morning, 9 or 9:30, I will share you a link for your numerical classes. Clear? So on the same day, I will provide that link early in the morning, 9:30 approximately. Fine, for 1 hour. Okay. So shall we start now?
Yes, sir.
Okay, fine. I hope the screen is visible now. Okay. So today we are going to start the another module, that is three-phase circuits. Fine. Before we proceed to a three-phase circuit, let us revisit the generation of electricity or generation of an AC single phase voltage and current. So we know that the equation of voltage is Vm sin omega t, and I is equal to Im sin omega t. So with the help of these equations, we can have voltage and current equations, fine, for a single phase system. So similar kind of equations that we can derive for three phase circuits. So three phase itself that says that there are three different equations of voltage and three different equations of current. Clear? So let's have a discussion about, first of all, what do you mean by three phase and what are the benefits of it. So first of all, three phase systems are most common connections nowadays in India, not only in India but all over across the world. Because if you deliver more amount of power from one place to another place, single phase is not enough, and for that we need a three phase system. Fine. So this is the most common use of three phase system. Then all modern generators are typically three phase. So whatever the electricity is generated are always three phase. And we know that three phase generation by revolving magnetic field created by three different phases, which are displaced at 120-degree apart from each other, and how electricity is. Yes, any question? Somebody's.
Sir, I just connected audio.
I mean, you mean
I just connect to the audio connection, so the mic was already.
Yes, yes. Fine, fine. Sorry. Okay, fine. I think screen is visible now, and my audio is also clear to you. Okay. So here, all modern generators are used this three-phase system, as well as whatever the power is generated is being transmitted through transmission lines are also connected in three phases. So this three-phase power generation and transmission and deliver at the consumer end. Fine. So here most of the industries need a three-phase power supply because the various equipments which are designed are based on three-phase system. Except our domestic instrument, domestic equipments like fan, tube light, and all single phase supply system. Right? So if there is a generation at this place, the electricity is generated and is being transmitted through transmission line in three different lines, and again there are some substations and then transmission and again substation and then transmission, and finally at our premises, if it is kind of apartment, then from this three-phase system, three-phase four-wire system, which is also known as a three-phase system, where the another R, Y, B, and neutral. So all the different apartments here are connected through R and neutral, Y and neutral, B and neutral line. Clear? So here we can convert from this three phase to a single phase with the help of connecting to the different phases at our department. And if there is an industry, if they require a three phase supply system, directly it is connected to a three phase supply system. We will also discuss about the neutral, why neutral is required in the system and what is the function. So basically there are two different types of three phase systems are available, that is three phase three wire system and another one is three phase four wire system. Clear? So here three wires are used and here four wires are used. Okay, we will discuss in detail about this later on, but these are the two most common connections which are there in system, that is three phase three wire system and three phase four wire system. So three phase three wire system is for balanced load or balanced condition, and this three phase four wire system, one more additional neutral wire is there and it is used for unbalanced system. So for balancing and unbalancing, that's what we are going to discuss. Fine. So there are certain advantages of his system, that is it is more efficient. How it is, we'll see in the next slide. It uses less material, also we'll see in the next slide. And it costs less than the single phase apparatuses. Fine. So how this different benefits occurs during a three-phase system, let us see in detail. Suppose if there are 6 terminals for 3 individual single phases, suppose if there is a one single phase, fine. So phase and neutral, then phase and neutral, then the third one is again phase and neutral. So here for this system, these 3 individual single phase systems require 6 connecting wires. One is for phase, another is for neutral, another is for phase, neutral, phase and neutral. So we need 6 wires. So in three phase system, either of these 3 terminals, these neutrals, are short circuited at one place and make a star connection. And with the help of this, named as R, Y, and B. So RYB and neutral. This 4 terminal system can be achieved with the help of connecting or shorting the 3 different terminals, and hence using 4 wires the same capacity of power can be transmitted even if we use it with the 6 different wires of individual 3 single phase systems. Clear? So ultimately that reduces the cost of wire. Fine. Even there are 6 wires make sometimes complicated circuits, and here with the 4 wires and with the help of 3 wires for delta connection it will be 3 wires, right? We will see later on. So these are the benefits of it. So all these 3 different connections like star and delta connections, which we are going to discuss, and the relationship also going to be discussed. And later on, we are going to have various types of connections. That's what we are going to study. Okay. Now let us see the generation of an electricity. So as in single phase AC system, the electricity is generated according to the Faraday's law of electromagnetic induction, like whenever flux cuts and EMF is induced in it, and the magnitude of the direction is given by Fleming's right hand. Clear? So here similarly, but instead of in construction, one winding, instead of that, there are 3 windings which are placed at 120-degree phase difference. Now you know what is phase difference, right? 120 phase difference are Y and B. So here there is a two pole machine. One pole is here, another pole is here, and here there are 4 poles. 1 pole, 2 pole, 3 pole, and 4 pole. Fine. So we can have multiple phases that we can connect. So suppose here, if there are 3 vectors acting simultaneously, so vector 1, we can write all these generating equations in the form of vectors also. Clear? So here there are 3 vectors acting at the same time. Which are these 3 different vectors? VR, Vy, and Vb. Clear? VR means the voltage of this phase, voltage of this, and voltage of this. Right. So here, with the help of these 3 different voltages, why we need to make a phase difference between these 2? Because ultimately we are going to have the 3 different equations of voltage. Suppose if all the 3 acting in a single axis, suppose if this is an axis, so your R phase, Y phase, and B phase are acting in the similar plane, then there is no sense at all. Fine. So by making this phase difference, we can have 3 phase waveforms. For single phase, we know that the waveform is one cycle here. Fine. Now similar kind of waveform, like this is R, blue also is there, and yellow also there on the same plane. We can say all these 3 are in phase with each other. Clear? And we know that if all these 3 are in phase with each other, then there is no phase difference here. But if we maintain the phase difference 120-degree, then we can have the 3 different waveforms R, Y, and B. So here we know that it is 90-degree, 90-degree, then 120-degree. So after 120-degree, another waveform, which is yellow in color, can be acted like this. And similarly, blue color, which is again at 240. So this is 240 and another similar kind of waveforms. So here we can have 3 different waveforms of voltage, VR, Vy, and Vb can be drawn with respect to time t with a phase difference of 120-degree each. Clear? Okay. Now we can write the various equations also. How? Let us see. So here, by keeping this phase voltages at 120-degree each, we can consider it as a balanced condition. Balanced condition. Because if there is a phase difference between the 2 quantities, then we won't say that the magnitude generated are same of all the different quantities. But here, by maintaining same phase difference, because we know that VA cos phi and V1 cos phi, V2 cos phi, and addition of all these vectors. Ultimately, you would be having an X component and Y component, and then the resultant voltage. Similarly, here there are three different voltages acting. We can have an X component of all these three, and we have a Y component of all of these. And finally, we can find the resultant of all these three induced EMF. So there are three different induced EMF R, Y, B, which can be written in a different form of equations. So equation number one is E is equal to Em sin omega t. Right. So that is your equation EA. So this is EA. Clear. And there is no angle here because it starts from zero. Clear. Now, similarly, this is EA. Now, in anti-clockwise direction, this is with respect to minus 120 and minus 140. Fine. So here you can write minus 120 or you can write in this fashion also. Clear. So either you can write. So for three-phase systems, normally it is written with minus 120 and minus 240 degree centigrade. Okay. So why 120? Because Y phase starts from here, like another phase. And similarly, the another phase starts from this. So there is a phase difference of 120 degrees. 120, 120. Clear? As I already explained. So we can write an expression EA that is for phase A, EB is that is for phase B, and EC that is for phase C. Clear? So we can write these three different equations and we can find the resultant of it. And this resultant is the final voltage value, or we can say the magnitude of all these three power phase connections. So we can have this phase difference 120 each. We can write three different equations, and these equations can be derived similar way of single phase. Fine. So this is a single phase, and because of there is a phase difference between these two 120 degrees, clear, we can write this equation in this way also. Clear. So just a minute. Okay, sorry students. So here this way we can have these different types of equations that we can write. Okay. Now, as I already conveyed that what are the benefits of these interconnections. So by making interconnections, we can save the wire materials which is used. Fine. So these are three single phase wire systems which can be connected either in star or connected in delta, because whatever the power is generated at generating station, generating station, fine. So the power is transmitted, and this transmission power up to the transmission or we can say the distribution system, up to distribution system, the power is transmitted in a balanced condition. But when the power from this distribution which reaches to our apartment, we can say the power is unbalanced. Clear. So this unbalancing, because at consumer end only it could be possible, at consumer end only possible that there is unbalancing, because this person can use the different power, this person can use. So here in these three different phases which are connected to the consumer, clear, that that maybe R phase, Y phase, and B phase having the different values of current. Okay, so here there is a system R phase, Y phase, and B phase, and there is a neutral. Right. So if you want to connect from these three phase to a single phase, so this is a one apartment, this is another apartment. So this one apartment can use the R phase connection and the retail circuit that is provided with this neutral. Yeah. And similarly, so we are simply converting into single phase. Right. So this way it is distributed here. Suppose if this want, you can connect it to the R phase also, you can connect it to Y phase also. So an electrician which connects all the different departments, they always balance, try to balance the load here. Right. But somehow the usage is not similar, and because of that there is an unbalancing system. So balance load and unbalanced load. So in balanced load, the amount of current flowing through these three different phases almost similar, and in unbalanced condition the amount of current flowing through these three different phases are different. Clear. So we are going to discuss about the various connections for this three-phase system. Clear. So what are the benefits? I think now it is known to you, and why three-phase system is more economical compared to three different single-phase circuit systems. Clear? Okay. Any question till now? Any question now? Okay. So EMF, which we found, that is for phase or VR plus Vy plus Vp. And if we write these equations and if we add these three, we'll get the answer 0 here. Like VRM sine omega t plus VRY or Vy maximum value sine omega t minus 120 degree plus minus 140 degree here. So if you sum all these three vectors with the method which we have already studied before, fine, we can get the value that is equal to 0 here. So summation of all these three voltages. Similarly, we can find the summation of all these three currents. The current flowing through three different phases, IR plus IY plus IB is equal to 0. As per the law, which you can apply, Kirchhoff's voltage and current law. Fine. So here, the summation would be 0. Now, based on this, we can have the different connections. First of all, if there are 6 terminals, and these 6 terminals where we can connect either in two different ways. One is star connection, as you are familiar, already studied during the experiments. So R, Y, and B. Fine. So if we connect all these three different other terminals, and if we short this would be your neutral point, and this would be your R, this would be your Y phase, and this would be your B phase. Fine. So here, this is a 3-phase 4-wire system. So normally star connection is applicable to the load where unbalancing is there. So this is B phase. So unbalancing, normally which is that which is at consumer ends. So our connections are always three-phase connections are always in star. So star where four different wires are used: R, Y, B, and neutral. Fine. So the similar kind of things can be redraw with the help of this way. And this point can be considered as neutral. So the similar diagram can be redrawn with the help of this star. So this is a star connection, and that is why it is known as star. So the starting end are connected with the phases, and the region end are short circuited at one point. So the current flowing through this, from this, and from this, that should be zero. Clear? So this is about star connection. Similarly, in delta, we can also connect in delta. And we can rearrange these three different phases in a delta fashion. Clear? Suppose if this is R phase, this is R phase, this is Y phase, and this is B phase. So we can consider as R1, R2, Y1, Y2, and B1, B2. Clear? So here, suppose if you consider that this is a R phase here, so R1, R2, clear? Then this is the Y, then Y2, Y1, Y2, and similarly B1, B2. B1, B2, or you can write B1, B2 here, B1 and B2, and Y1 and Y2 here. Clear? So by connecting this, so here which two different terminals are shorted? R2, B1. So R2, B1 is shorted like this. Clear? Similarly, this B2, which is shorted to Y1, so B2, Y1 like this, and like this. So this way, if we connect and if we take three different terminals out from this, clear, then this is RYB connections. And if we rearrange, we can rearrange in the form of delta connection. Fine. So there are basically two different types of connections, delta and star. So whenever there is a balance system, normally a delta connection are used for load as well as for transmission system. Okay. Now let us see in detail about these connections. Okay. So as I told you, the star connection, fine. Now these star connections are having a different relationships. Fine. So first of all, let us see. I may draw in a different way so you can understand with the different colors. So red phase, fine. Y phase. For Y, I may use the different color like green. So this is Y phase. And we have okay. Now let us try to understand the line voltage and phase voltage, and let us try to understand the current, phase current, and line current. Okay. So here there is a neutral from this point. Now we can use this connection for both the conditions, whether whether it is balanced condition, whether it is unbalanced condition. Let us see how. So here they have written that the equation of IR plus IY plus IB is equal to 0 here. That means the amount of current flowing through this would be same. So if the current same, then neutral wire is not required. So there is no current from this. If the current IR, current, what we can say IY, and IB are similar or kind of same current. If current are same according to Kirchhoff's current law, the algebraic sum is zero at this point, and no need to. I mean to say, no current will flow from this neutral. Clear? But instead of that, if the current is different, IR, IY, and IB, clear, then there would be a possibility that there is an unbalancing at this system and it would not be zero. And for that, we need to flow the written path to close the circuit. And this is the requirement of neutral of the system. Clear? So, based on this line and neutral, so obviously there are two different types of voltages. One is known as line voltage and another is phase voltage. What do you mean by line voltage and what do you mean by phase voltage? Let us discuss. So line voltage, that is always between two different lines. So this is line R and this is line B. Clear? So if we write the voltage is between two different lines. Suppose if there are two different lines, R and B. So here the potential difference between these two is known as line voltage and it is abbreviated as VL. Specifically, if you want to abbreviate, then if it is between R and B, then we can write VBR or VRB voltage. So this is the line voltage. Similarly, another voltage between R phase and between Y, that is known as VL, or we can say the voltage between R and Y. And similarly, we can have another set of voltage between Y and B, that is also VL, or we can say VYB. VYB. Clear? So line voltage is always between two lines. Okay. Now, what does it mean? This is a load, maybe inductive load, maybe a resistive load, maybe a capacitive load. So I can make this star with a resistor load also. I can make this star with a capacitor load also. So we can have a different types of load, but the abbreviation which named as VL, that is VBR, VRY, and VYB. So throughout the whole chapter, I am going to use this abbreviations for line voltages. Okay. Now we know that the power is going to be consumed here in this. So here there is a voltage drop between these two terminals. So this is nothing but a phase. And if you look at the connections, one is connected, one terminal of this load is connected to a line and another is connected at the neutral point. So this is the neutral point here. So the voltage between a line and a neutral, that is known as phase voltage, because this is phase number one, or we can consider it as phase R. This is phase two, or we can consider it as a phase Y. And this is blue phase, or it is also three number term. So here the voltage between any line. So this is line number one, and the another terminal which is connected at the star point and neutral is connected. So always we try to understand the voltage between line and phase is always abbreviated as phase voltage, and it is abbreviated as VPH. VPH. And similarly, we can also write is equal to VRN, where R is a line which is connected and N is the neutral. So phase that can be represented with VRN also and VYB. So here if I use a terminology N here, then you directly may consider that this is the voltage drop or voltage across the load which is connected either in star fashion or delta fashion. Is that clear? Is that clear? Okay. Now, there are different types of relationships between phase voltage and phase line voltages. So let us see. Suppose if these are three different phases. Now see, this is a line voltage. I will abbreviate it as VL right now. We will not be specified right now. Fine, voltage. And what is the voltage across this? That is VPH. So across this, it is VPH. Across this is VPH. We can name to with the different, right? And across the different lines, there are different line voltages. So always there is a difference of line voltage and phase voltage. Now, if you look at between these two terminals, terminal R and terminal Y. So here, the current flow, which is IR, also known as line current, IL, line current, and similar current will flow from this phase also up to this point. Clear? So we can say IR, I. So ये phase में से जो current flow that is also known as phase current. Is also known as IPH. So current flowing through this phase that is known as IPH. So here for star connection, we can say IR is equal to IL is equal to IPH. So similar current will flow from line to phase up to neutral point. And similarly here also. So we can say in star connection, line current is equal to phase current, isn't it? So now what is line current? What is phase current? The current flowing through the line is line current, and current flowing through this phase is known as phase current. Clear? So we can say line current IL is equal to IPH, and this is the simplest way to remember this relationship between different currents for star connection. For star connection. Now, similarly, let us see the difference or the equation of voltages. The equation of voltages. Okay. Now, this is R phase. This is VPH. This is VL. This is also VPH. Now, if you look at this circuit, for a time being, if you remove this third phase here, clear, for time being. So, can we say that this VL is equal to VPH? No, because here at this junction, that there are certain voltages, two different types of phase voltages acting across this VL. So always there would be a relationship between VL and VPH. And what is this relationship? That is VL is equal to root 3 times VPH, that we can derive with the help of phasor diagram. Okay. So first of all, try to understand there is a relationship between line voltage and phase voltage, and that is root 3 times. So we are going to derive this theory later on, right? But looking at the circuit, we can say the relationship between line voltage and phase voltage is always there in star connection, are not similar, are not equal. But the current flowing through each line is also equal to the amount of current flowing through the line. Is that clear? Okay. Similarly, here sometimes, the phase voltage VPH is also written as EPH. So here you can say this is a neutral wire and this is a line R. Clear? So the voltage between these two, it is also sometimes written as ER. Why I'm mentioning this? Because in different books, if you refer, different notations are written. सर आपने VPH बोला था, यहाँ पे ER लिखा है. We don't understand. So that's why I am just, for your understanding, I am just saying all these notations here. Right? So this ER is also, again, by looking at this too, this is a neutron. So R, Y, N, you can also write an as V, R, N, B, P, H, EPH, and ER. So these are the four different notations are used for a single similar kind of notations. So don't be confused while reading or referring the different books. Clear? Okay. So if you refer BL Thereja, different notations are there. If you refer your Patel book, Tetrai, then the different notations are there. But ultimately, the meaning is same. Fine. So this is star connection. Now let us see the delta connection. We will discuss about this afterwards. The relationship and derivation of this line voltage and phase voltage, line current and phase current for star. Now let us try to understand the delta connection. Fine. So application of delta we have already discussed. When there is a balanced system, normally these kind of connections are required. Why delta and star connections required? Because ultimately it reduces the number of wires used for transmitting the same amount of power. Here, instead of 6 wires, we can use 3 or 4. Clear? So this is a benefit of transmitting the power without any complex circuitries. Okay. So here, looking at the first instant here, the sorry, VRY, VBR, and VYB are line voltages. Line voltages. Clear? And here, the current flowing through this, that is line current, IL. But here, at this point, the current is going to be divided into the different areas. So current may be flowing from here to here, as the arrow shows. Fine. So you can consider that this is phase current. Phase current means the current flowing through this phase. And this is line current flowing through this line. Clear? So here you can say, suppose if 10 ampere current flows, so 10 ampere current will be divided into two different branches here. Clear? It means line voltage and phase voltage are not same here, not same here in delta connection. But what is the difference? There is a relationship IL is equal to root 3 IPH. That is what we are going to derive. Now, what about the voltages? So voltage across this phase is VPH or EPH. This is VPH. This is also VPH. Now here if you look at the line voltages. So what is line voltages here? And for a time being, if you remove this circuitry, this circuit, this one, you can say the voltage VRY is exactly connected in across this phase VR and this phase. So whatever the value of voltage VRY, similar value is also across this because it is connected in parallel lines. So in delta connection, always we can have the line voltages VL or VRY, fine, that can be written as VPH phase voltages for delta connections. And there is a relationship of IL is equal to 3 times IPH for delta connections. So try to understand, try to recognize that what is line current, what is phase current, and what are the relationship between delta connections and for star connections. Clear? Because ultimately we are going to use it for numerical solution. Clear? Now, this is four different terminologies which we have discussed, which we are going to derive. Okay, so for star connection, so symbol for this sometimes it is used like this also, star connection. Sometimes it is also written as Y connection. Sorry, still there is an issue with the handwriting. Y connection, fine. So if it is asked in examinations like Y connections, so don't be afraid of it. Clear? Y connection is a star connection. Okay, and for star connections, looking at this, simply you have to remember one relationship, that is line current, and this current flowing from this, that is a phase current. So if you draw this figure in your rough page, you can easily write four different relationships. IL is equal to IPH, and then if it is similar, then VL is equal to root 3 times VPH. In the next lecture, we are going to derive this expression. Fine. And what about delta connection? So looking at the figure here, the line voltage is always equal to phase voltage. So we can write VL is equal to VPH. And there is a relationship between current because the current line current is not similar, which is flowing from this. So IL is equal to root 3 times IPH. Okay. These four relationships, out of this, there is no need to derive the equations for these two different equations, equal equations. But VL is equal to root 3 VPH equation will be derived for star connection, and IL is equal to root 3 IPH equation will be derived for delta connection in the next lecture. I hope you enjoyed this video session today. Any question if you have? Otherwise, we can stop this session right now. Any question?